All right, so today we are going to be doing a lesson on fluid flow and Bernoulli's principle. So first, when we're looking at fluid flow, fluid can either flow quickly or slowly, and that's because when a fluid like water or syrup, maple syrup, flows, there's different internal molecular forces. And if you have very strong internal molecular forces, you have very, very high internal frictional forces which resist that motion, which resist that flow. And if you have weaker intermolecular forces, then of course less friction and you can move faster. And so this results into what we call viscosity. We've learned that term in science over many years. Viscosity just means high internal resistance or high internal friction. And something like honey or maple syrup or molasses would have high internal friction and therefore a high viscosity. Whereas water, for example, has very low viscosity because it has very low internal friction. Okay, but temperature also changes the amount of internal friction or viscosity. Generally in a liquid, when the temperature increases, you get a lower viscosity. However, it's the opposite in gases because when you tend to increase the temperature, you get more particles colliding with each other. But we don't usually just have a fluid flowing on its own. For example, in this case, you can have a fluid flowing in a pipe. Now, you're going to have external frictional forces as well. Specifically, the fluid that's close to the edge of the pipe will feel those external frictional forces and will be moving slower than the fluid flowing through the center of the pipe. But as long as the fluid's moving slow enough, you can have adjacent layers of the fluid flowing smoothly over top of one another. If that is happening, that is what we call laminar flow. And it's, of course, what we want when we're designing objects to be able to go fast. Why? Well, if we don't design objects to go fast, which we call streamlining is designing objects to keep laminar flow, you end up with turbulent flow. If you go too fast, right, those layers, adjacent layers can interfere with each other, which then results in disturbances and turbulences, which gives you these sort of eddies or vortices. And those vortices can actually remove kinetic energy as it changes it into, say, thermal and sound energy. And so they slow you down. And if you're designing a vehicle, or whether it's a car or a train or a submarine, whatever, if you're designing something to go fast, you need to design it, you need to streamline it very well so that you maintain laminar flow. And there are different ways that we can do this, other than, of course, the shape of what you're designing is one way of doing it. Another way is liquid plastics. We've learned that one way of reducing turbulence in liquids anyways is to add this liquid plastic to it. Maybe not so great for the environment though. Okay, but the biggest way we do it is engineers look at the actual structure of the object. Right, just like I showed you with that previous car. I mean, I'm sure you can understand what it would mean if you put this car up against, say, a car that's shaped like a cube. I think we all know which car I'm talking about here. This car is obviously meant for city driving if it's shaped like a cube, as opposed to high-speed highway driving. High-speed highway driving in a cube would cause a lot of turbulent flow, which reduces your speed, and therefore you need more gas to be able to just keep that speed. So those cube cars are not very efficient on fuel for highway driving. Okay? You want something that's more streamlined to be able to go faster without losing fuel, to have good fuel economy. Okay, things like buildings, of course, engineers have to look at that too, because high winds that hit the building can cause turbulence around the building. Right? If it's hitting the building at multiple angles, that could be dangerous to the structure of the building. So they have to be very careful on when they're designing the building. I'll just pause it there. All right, so if we're good, let's try our first problem. Now this is on our Jamboard, which again is linked. I put up the actual handout here. And so let's look at the first question, which is going over some definitions, making sure we understand them. So the first one says resistance of a fluid to flow. All right, so resistance of a fluid to flow, that is our viscosity. Flow in which adjacent regions flow smoothly. So type in the chat, do you think it's eddies, laminar flow, or turbulent flow? Okay, if you have adjacent layers flowing smoothly over one another, we call that laminar flow. What happens when those layers cause disturbances and resist the fluid flow? That's our turbulent flow. And eddies, process of elimination, those are the whirls in the flow of fluid. Okay, next, this is just based on common knowledge. Rank the following liquids in order from low to high viscosity. Okay, I'll just pause there. All right, so we ranked it from low to high. Low meaning it can flow the easiest, the skim milk, then whipping cream, again, assuming it's not whipped yet. And the highest would be honey, flowing quite slowly. Okay, so let's go back to the PowerPoint. We're going to go over something called Bernoulli's principle. So before we get into that, let's first look at this pipe. This pipe all of a sudden reduces its cross-sectional area and becomes, well, smaller. Now when that happens, the water actually speeds up. And this is by something that we call the continuity principle. The continuity principle says the same amount of water must flow through the same cross-sectional area in the same time. So if you look at, like, just draw a line here and think of, okay, if a certain amount of water makes it through that line in a certain time, the exact same amount of water must make it through this much, much smaller area in the same time. Only way for that to happen is if the water is moving a lot faster. Right? And I'm sure you've all realized that. So if you go outside and you take a hose and you put your thumb over it, right? You put your thumb over it there, you can go then shoot your sibling with water. Right? It goes a lot faster, and so you get it going farther. That's pretty much with common sense. But what I find is against common sense is this. Now this is kind of a what we would call a Venturi meter. So here we have a large diameter and then it gets smaller. Now we know it gets faster here. That's what we just talked about. But if we were to place tubes, you'll notice that there's a difference in pressure. Okay? There is actually more pressure in the larger tube because it's pushing up further against our atmospheric pressure than in the smaller tube. This goes quite against common sense because a lot of people, especially ones who've taken a lot of chemistry, say, well, no. If you take a container of, like, say, a gas and you reduce the size, you increase the pressure. And that's 100% true. Of course, you take a container of gas, you reduce the size, you've increased the pressure. But that's statics, meaning that gas has nowhere else to go. This is fluid dynamics. The fluid is moving through the tube. It's not confined to a certain volume. It's moving. And in this case, when we get an increase in velocity, we get a decrease in pressure. So think of it like this. Let's say you're driving and you've got cars in front of you and cars behind you. And they're very close to each other. You're just starting to get onto the on-ramp onto a highway. Now when you get onto the on-ramp, the car in front accelerates, hits the gas, and moves away from the car behind it. And then the car behind it accelerates. And then the car behind it accelerates. And they all accelerate. But as they all accelerate, because of that sort of delayed reaction, the spacing between them increases. And it's almost like you can think of that same thing occurring in the liquid, which would reduce the pressure, right? Less things crammed up against each other. The basics for Bernoulli's principle. So Bernoulli's principle says when the speed of the fluid is low, the pressure is high. And when the speed of the fluid is high, the pressure is low. And there are applications of Bernoulli's principles everywhere. And this is one you can even try at home, since we're all at home. If anybody has like a ping pong ball and a hairdryer, what you can do is put the ping pong ball over top of the hairdryer, point the hairdryer up, you can put the ping pong ball on top. And what happens is, because the flow of air around the ping pong ball is high, the pressure on the outside is high, where the pressure on the inside is low. And so the pressure always goes from areas of high pressure to low pressure and pushes inwards from the sides and keeps that ping pong ball in the stream. It doesn't go flying off to the side. It looks like a magic trick, like, oh, how are you doing that? But it works every time, thanks to physics. This is also how planes fly. Right? Now, when a plane flies, right, you have the wings can increase or decrease their angle of attack. And let's say a wing starts pointing down. Well, you can think of this also as Newton's third law, as it basically just the air going off the wing ends up being pushed downwards, which then pushes the plane up. But what happens is, according to Bernoulli's principle, is the air going over the top, due to something called the Coanda effect, actually pulls the air down the wing and fast. And so the air going above the wing moves faster than the air going below it. And so we have an area of low pressure above the wing and an area of high pressure below the wing. And since everything wants to move from high pressure to low pressure, it gets pushed up and we have lift. Okay, there's also a lot of other situations. If you've ever been in a shower and got annoyed that the curtain keeps moving in on you, well, you can't avoid that unless you actually turn off the shower, right? Because that high speed of the water coming from the shower creates a lower pressure inside the shower than outside. And so you get the shower curtain pushed from the outside from high pressure towards the inside of low pressure. You can't avoid it unless you turn off the shower or put magnets on your shower curtain, right? Same with a vacuum. A vacuum has a motor on the inside, which, well, causes the air inside the vacuum to increase its velocity, creating an area of low pressure, which creates sort of a suction from the high pressure outside the vacuum to the inside where we have low pressure. Okay, so lots and lots of different applications. I'm going to stop there, but I'm going to show you a video which is going to go over another application, which I highly recommend you watch.